Hello students, today's topic is Fajan's rule. So before explaining the Fajan rule, what we are going to do is that we will first try to understand how actually a chemical bond is formed. So basically, we can assume that there are two atoms, there is atom A and there is atom B. Okay. So when atom A and atom B, they come in contact with each other, they form the chemical bond by two methods basically. We can say that either there will be transfer of electrons, and when there is transfer of electrons between two atoms, the ionic bond is formed. Or we can simply say that there will be sharing of electrons, and when there is sharing of electrons, the covalent bond will be formed. Okay. So when the bond is actually formed, the atom A and the atom B, they both applies force of attraction on each other and force of repulsion on each other. And how it is going to operate basically. So the nucleus of atom A is going to attract the electrons of atom B, and the nucleus of atom B is going to attract the electrons of atom A. And in this process, the electron cloud of atom B is going to distort by the nucleus of A, and the electron cloud of atom A is going to distort by the electron cloud of the nucleus of atom B. So basically, in this case, because of the electron distortion, okay, there will be the movement of electrons towards the atom. Now in this case, what we are going to do is that in Fajan rule, we are going to see which atom will be more able to attract the electron cloud of the other atom basically. So in Fajan, what we are going to study is that the polarization, the ionic character and the covalent character in a chemical bond. Now we are moving further to the next slide. We can simply say is that the Fajan rule, it describes the condition under which a chemical bond is more covalent or more ionic in character. This is the same thing that I have explained to you before. Now, the chemical bond, it is basically classified in two types. The first one is the ionic bond. So now, in ionic bond, what we can say is that there is complete transfer of electrons, and when there is complete transfer of electrons, the transfer of electrons is between two atoms. So the atom which is giving electrons is termed as the cation, and the atom or the molecule which is accepting the electrons, it is termed as the anion. So in order to form an ionic bond, there will be high electronegativity difference. And what we actually mean by the high electronegativity difference, if we see the example, the Na and the Cl, the compound is NaCl basically. So in NaCl, the electronegativity of Na is 0.93. and the electronegativity of Cl is 3.16. So if we draw the difference basically, so 3.16 minus 0.93, and the difference will be around 2.23, I think, maybe. Okay, so the difference is 2.23 here in case of ionic bond. If the electronegativity difference is between 1.7 to 2.2, then the bond is termed as pure ionic bond. So our third point is there, the non-polarized bond. Okay, so the bond will be completely ionic. Now if we move towards the covalent bond, in covalent bond what actually happens is that there will be sharing of electron. The electronegativity difference will be low. And what we actually mean by low electronegativity difference, in case of AlCl3, if we calculate the electronegativity difference, it will be around 1.6. So if the electronegativity difference is less than 1.7 and it is between 0.4 to 1.7, then in that case that chemical bond will be a covalent bond. Okay. Now in this case a molecule will be formed, and what we actually seeing here is that it is highly polarized. And what we actually mean by highly polarized, the two electrons of the electrons of the two atoms basically, they are overlap with each other. So there will be sharing of electrons basically. Ionic and a covalent bond is formed basically. Now if we move back to the Fajan's rule, what it is saying is that it describes the conditions under which a chemical bond is more covalent or more ionic in character, and they relate to the degree of polarization of anions by the cations. Okay. Now in ionic bond, if it is a pure ionic bond is there, so there will be no polarization. Okay, so the polarization of anions is done by the cations. Now in the next slides we will see how this thing actually happens. If we see here is that The polarization, basically what it is, so it is distortion of electron cloud of anions by cations. How it is actually happening is that this cation, basically whatever the cation is there, for example if we are assuming that it is Li positive, okay, for example we are taking here example of the Li positive, and the anion is I minus basically. So the lithium ion, it is basically very small in size. So due to small in size, what actually happens is that it is going to attract the electrons of the anions, and when it is going to attract the electrons of the anions, the electron cloud of the anion is coming in close contact with the cation, and when it is coming in close contact with the anion, there will be overlapping of electrons, or we can say that there will be overlapping of orbitals basically. So in that case there will be a formation of a covalent bond. Okay, now if we move back to the slide, what is polarization? Basically it is distortion of electron cloud of anion by the cation. We are seeing here is that why it is happening, because of the high nuclear charge of the cation. The second thing actually happening here is that the polarizability, the ease with which anions of the electron cloud is distorted. So basically if the size of the anion is bigger, then in that case we can distort the electron cloud of the anion with the help of a cation. Now the polarizing power, basically it represents the ability of cation to distort the electron cloud of anion. So this is the whole concept of polarization. Now moving to the next slide. What are the Fajan's 4 rules? Basically, the first rule is the cation should be smaller. If the cation is smaller, then it will have high nuclear charge, and if it is having the high nuclear charge, then it will be able to distort the electron cloud of the anion. Now, what are the examples that we are having? Li positive, Na positive and K positive. We are seeing here is that moving down the group, the atomic size or the ionic size increases basically. So in this case, we can say that the Li positive has more polarizing power in comparison to the Na positive and K positive. So smaller the cation, greater the polarizing power, and more will be the covalent character. Moving to the second rule, large anion. If the size of anion is larger, then in that case there will be more polarization. So basically I minus will be more polarizable in comparison to Br minus, Cl minus and F minus, and if there is more polarization, then there will be more covalent character. Moving to the third point, high ionic charge. What we actually mean by high ionic charge, if we see here is that Al3 positive, its charge is plus 3, Mg2 positive, charge is plus 2, Na positive, charge is plus 1. In these 3 ions, the number of electrons are same, but what is the major difference here is that as the cationic charge increases, the size becomes smaller. So basically, higher the charge on the cation, greater will be the polarizing power, because the size is becoming small, the effective nuclear charge is increasing, so the polarizing power will increase, and as a result of that, the covalent character will also increase. Fourth point, the pseudo noble gas configuration. What is pseudo noble gas configuration? Though electronic configuration which is similar to the noble gas, but it is not actually a noble gas configuration. How we can say that? If we take an example of Cu positive, what is the electronic configuration of copper? So basically for copper, the electronic configuration is argon 18, 4s1, 3d10. If we are converting it to copper positive, then in that case we are removing one electron from the outermost shell, that is the fourth shell. Now the configuration will be 3d10, and if I am expanding the electronic configuration of argon, then it will look like this: 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. The third shell of the copper, it has a total of 18 electrons, and if the outermost shell of an ion has 18 electrons, then the configuration is termed as pseudo noble gas configuration. And if what actually happens is there is that if the cation has 18 electrons, then it has more polarizing power than the cation having 8 electrons. So if we compare the polarizing power of the Cu positive and Na positive, then in that case we see that the copper positive has more polarizing power. So what are the example? Basically, if we are taking the example of CuCl and NaCl, then we can simply say is that CuCl has more covalent character in comparison to the NaCl. So these are the 4 rules of Fajan's basically. Now we are moving to the next slide. Okay, so effects of cationic size and anionic size. So basically, lithium, it is smaller in size in comparison to the Na positive and K positive. This thing I have explained you before. So basically, smaller the cation, now what the slide says, smaller the cation, then it will have higher charge density, and because of the higher charge density, there will be stronger electric field, and because of the stronger electric field, there will be more distortion of the electrons of the anions basically, and because of that, there will be more covalent character. Okay, now moving to the next section, the anionic size. As the anionic size increases, we are seeing here is that larger the anion has electrons farther from the nucleus. We can simply say is that if this is a nucleus, for example, we are considering this is a nucleus, okay, for each and every atom, so the distance is large. So in this case, the electrons are far away from the nucleus, and if the electrons are far away from the nucleus, then in that case, it will be easier to distort them. It is okay. Now, what here is that electrons are loosely held, okay, then they are easily polarized and electron cloud distorts more easily, and there will be more covalent character. So we can simply say is that as the size of anion increases, the covalent character will increase. As the size of cation will decrease, the covalent character will also increase. Okay. Now moving to the next section. Rule 3rd, ionic charge. So higher the charge on the cation, more will be electric field. How we can explain here is that the charge density. Basically, what is the formula for charge density here is that okay, so charge density is charge by size. How we can explain? For example, if we are taking the example of Al3 positive, so the charge will be +3 and the size will be its ionic radius basically. So we will put the value here, then we can calculate the charge density. This charge density is actually represented by phi. It is also known as ionic potential. It is also known as ionic potential. So in this case, higher will be the charge density, thus higher will be the polarizing power. So Al3 positive is higher charge density in comparison to the Mg positive and Na positive. So we can say here is that AlCl3 is covalent in comparison to NaCl. Although Al is a metal, chlorine is a non-metal, the bond should be ionic, but because of the polarization, the AlCl3 bond, it is covalent bond. Now moving to the rule 4, the electronic configuration rule. What we are seeing here is that the 2p6 configuration of Na positive, it is a noble gas configuration. The 3d10 configuration of copper positive, it is a pseudo noble gas configuration, and the pseudo noble gas configuration ions has more polarizing power in comparison to the noble gas configuration. So Cu positive, it will have more polarizing power in comparison to Na positive, and the similar fashion Ag has more polarizing power in comparison to the K positive. A question will be there, the AgCl or KCl which has higher ionic character basically. So we can say that KCl has higher ionic character and AgCl has higher covalent character, because the polarizing power of Ag positive is much higher in comparison to the K positive. Okay. Moving to the next slide. Okay. Some important comparisons which are important in terms of JEE basically. So NaCl versus AlCl3. Basically, Al3 positive, it has more polarizing power. So AlCl3 will be more covalent in comparison to the NaCl. The next comparison is between NaCl and CuCl. The same pseudo noble gas configuration is there for Cu positive. So due to the pseudo noble gas configuration, CuCl will be covalent. Moving to the next example, basically AgF and AgI. Now Ag is the common. The difference is between the anion. So F minus and the I minus has bigger size, and due to the larger size, it will have more covalent character. Okay. So LiF versus CSF. Li is smaller in size, so Li has higher polarizing power, and if it has higher polarizing power, then in that case LiF will be more covalent in comparison to CSF. If we are moving toward the MgO and MgS, in this case similar, S2 minus has bigger size. Then in case of FeCl2 and FeCl3, Fe3 positive has smaller size in comparison to the Fe2 positive. So FeCl3 will be covalent, MgS will be covalent. So what are the key insights here is that more is the polarization, so more will be the covalent character, and because of the more covalent character, the melting point will be lower. The compounds will be more soluble in organic solvents, and they have more directional properties. Because why the directional properties are higher? Because the covalent character is increasing. As the covalent character increases, the directional properties of the bonds will increase. Okay. Now moving to the last section. Okay. So what are the properties that are actually affected by the polarization of the ionic bond? Basically we can say that the polarization of the anion. So the first property is the melting point. As the covalent character increases, the melting point will decrease, because the covalent forces are weak forces in comparison to the ionic bond. So what it says here is that more is the covalent character, weaker will be the electrostatic forces, and if the electrostatic forces are weaker, then the melting point will be lower. So LiF, LiBr, LiCl, Li has more covalent character, LiF has less covalent character. So in this case, LiF will have higher melting point in comparison to Li, and this will be the order. Now moving to the next section, the solubility. As the covalent character increases, the solubility in organic solvents will increase. Okay, so covalent compounds dissolved in non-polar organic solvents, we are aware of this thing, and solvents. And if we are taking the example of AgCl, what we are saying here is that AgCl is insoluble in water, but it is soluble in ammonia. When we are dissolving AgCl in ammonia, then in this case there will be formation of a compound AgNH3 whole twice positive, and this compound is actually known as Tollin's reagent, okay, which is used to distinguish between majorly we can say that between the ketone and the aldehyde basically, and it is also used for different things, basically for the detection of the ethyne, basically we can say that the detection, okay, the terminal alkynes basically is there. Okay, now the color, how the color is affected. As the covalent character increases, the intensity of the color increases, and what are the examples here is that AgF is white, and if we are considering the example of AgI, then it is yellow in color. And we can say there is that the AgCl, it is also somehow colorless, or we can say white in color, but because of the more polarization in the AgI, the color character increases and the intensity of color will increase. Okay, now moving to the third, the thermal stability. As the compound becomes more covalent, the thermal stability will decrease. Okay, now the example here is Li2CO3 and CS2CO3. So we can say there is that Li2CO3 decomposes more easily in comparison to CSCO3, because more is the ionic character, more will be the stability. So cesium carbonate will have more thermal stability in comparison to the lithium carbonate, because lithium carbonate is somehow more covalent in comparison to the cesium carbonate. Moving to the hydration enthalpy, as the size is smaller, the hydration enthalpy will be higher. So Li positive, Na positive and K positive, Li positive is higher hydration enthalpy, because what here we are saying is that K positive being less polarized. So what are the full line here is that what we are seeing here is that smaller the cation, higher will be the hydration energy. Okay, now moving to the next part, electrical conductivity. So as the ionic properties decreases, the electrical conductivity will also decreases. Okay, so covalent compounds are poor conductor of electricity, we are aware of this thing. Okay, so AlCl3 is covalent. So if AlCl3 is covalent, then it will be poor conductor in comparison to the NaCl. We are aware of this thing that NaCl gets dissolved in water. Okay, so it will have higher conductivity in comparison to the AlCl3, which is more covalent is character. Okay, so these are the properties, and these types of questions are going to come in the exam. Okay, thank you.